right, there you go.
Excellent. Thank you so much, organizer, for the opportunity and for you attending this session. So my talk is going to be a little bit different than previous one. It's very focused on one module, the computational tools, waveome, that helps to analyze and characterize the dynamics of omics in general and apply to metabolomics to show the patterns we see in the longitudinal studies. So I don't think I need to explain why the proteomics and metabolomics are important, but this figure shows there are many studies in the research that they use metabolomics and proteomics. In the first plot that we show the year and the number of publications. In the bottom one, we show the metabolomics used in different health conditions, and we see there is an increase in metabolomics. So if we focus those studies for different omics and we look at the metabolomics, we see there is a lot of longitudinal studies that they have time component in them, meaning that they have used the metabolomics data being measured over time to investigate the health conditions. So there are two general type of studies, at least in my group, that we have investigate the metabolomics. One, to characterize the health conditions. For example, in pregnancy, we didn't have a health condition. We just want to see how the microbes metabolize, they evolve over time. And in the second one, we look at the ISMB data, where we look at the health condition and you want to see how the metabolites are associated with the health conditions. So these are two different type of studies that you have the time and you have measured metabolomic data over time. So the question that we want to address in these tools is, if you have measured different omics, especially of metabolites over time, what are the patterns you see in your data over time and what explains those? For example, in the first plot, you see there are patterns that they are explained by the person. And in the second one, you see there are patterns that they followed almost the same pattern for different people and could be explained by the health conditions. So our goal here is to define to introduce this waveome software that tries to capture these patterns of changes over time and say what explains those changes. So a PhD student in my lab, Alan, and supported by a postdoc and a collaborator, Jason and Ariza. So those two, they helped to develop this framework. We call it waveome. And here I'm just trying to start with the input data. So what you see in the input. So let's say you have some information about your samples. One of them is time that you have collected the sample. One is the treatment. And Y is here, Y1 to 2. And usually Y is many of them. If they are metabolites, like about 20,000 metabolites, you have those. And you have measured them in this format. So this is the input data format. The waveome, what it does, it tries to characterize the dynamics and their associations. So what that means, if you look at the plots that I have in the right, this cartoon shows what are the type of dynamics we are looking at. For example, in Y1, let's assume it's a metabolite 1, and you see the pattern explained by the ID, the subject ID, who we have measured this metabolite from. The second part shows a pattern in the Y2, which is a metabolite 2, and we see the pattern is explained by treatment. So let's say you have two treatments, and the metabolite dynamic is related to those treatments. So these are very simple cartoon that explains the patterns, but these patterns, they can be very complex. And if you look at the two last subplot here, one of them shows the linear overall changes, which it could be linear and could be two different linear changes. And the last one could be the treatment. So the temporal dynamics is very complex. So what we are doing in the waveome software, we try to capture these patterns. And the way we do it, we use the Gaussian processes as a framework to capture these patterns. And what it does, we use the Y as the metabolites that as output or the outcome, and X are the metadata you have in the study. And the good thing about the waveome is that you can plug in all this data in it, and it tries to find these patterns in your data. So a simple version of the framework is this. So you have two inputs here in the framework. One of them is the prior kernels, which are the dynamics that you expect in your data. So I have received this question, so how we know what are the prior? So this is a very general type of kernels or patterns that we expect to see in our data, and almost covers any type of patterns you have in your data. This helps with the computational part when we define them. And the user doesn't need to specify those kernels. And then the observed data. So you have a data that you see in your study, which is the metabolite profiles in your study. So you have those, you plug them in as an input to waveome. What the waveome does, it tries to find the kernels. And this is the main part of the waveome, tries to find the kernels. They are the dynamics what they are in the data and what explains them. And what you see as the output, those are the two major output of the waveome. One is the pattern you see in your data. For example, in the bottom, you see a pattern that explains what is the major pattern in your data, and the left one. And the right one is the residual, what is not explained by that pattern. So you see two plots there. And the top part is the hyperparameters that defines those kernels in the data set. All right, so I'm just going to show output, and I know I have a short time here, 10 minutes. I'm trying to cover everything. So here is a study, one of the studies. Many of the study in my group, we focus on metabolites and microbes. And this is one of the longitudinal study. We want to characterize how the microbes and metabolites, they change over time and how they are associated with the clinical information we have about those individuals participated in our study. So as you see the data and the time points, they don't need to be even. So many missing data. In the bottom, I'm showing the collection of the data. And so we have the breast milk microbiome, and from the infants, we had the stool samples, and we measured the microbes and metabolites. I'm going to focus on metabolites and showing the outcome for that from the waveome. So this is, we try to visualize the outcome from the waveome, what it gives you in the rows. Those are the kernels or the dynamics that waveome reports, or the patterns that it sees in the data. And then explains what are the metabolites that they follow those patterns. So this heat map is basically are the prioritized kernels or the dynamics in the data, and the columns are the metabolites that they follow those patterns. For example, the very simple one that I highlighted here is the pattern, that is squared exponential pattern, which is a kernel explained by age at the stool sample collection, which is represent the gestational age as well for us, and the vitamin A. And this pattern we see is associated with this kernel is mostly explained for the vitamin A. So as you see, the outcome of the waveome has two major outputs. One is the dynamics or the temporal dynamics, if you have the time, explains what are the patterns you see in your data and what explains those patterns, and what are the omics data associated with those patterns. And we show it as an outcome, a direct outcome from waveome as a heat map. Here we threshold to some of the high rank patterns in the data, so you can use the waveome to generate this heat map and threshold it in many different ways. So our tools, waveome, is very generic, meaning that you can apply it to any omics data. So here I'm just showing for the same study, applying it on the microbiome data. And we see that there are microbes that they are associated. Here the columns are the microbes, and the rows are the kernels that we see in our data, so the dynamics that we observe. For example, like we say categorical index, these have an explanation in the software that says that this kernel is explained by index, the subject ID, or the person that we have collected the samples from. And then we can look at how these patterns are explained, the residual versus the pattern explained by the kernel. So these are different microbes, for example, and that they are prioritized by the software, and it explains, for example, this microbe is very person-specific over time. So to conclude this, waveome is a Python package. It's available online. You can install it. It has many examples. I just highlighted where you can go and find the examples. It's an IPython notebook at the moment, so you can just plug in your data, meaning that you need to read your data in the format that waveome accepts, and the rest of the steps are very clear. You can just run them and see the result. So we have multiple studies for multiple examples for different studies. So you can pick one from those that is more close to what you have and then run the software. So in summary, I showed that the metabolomics, there is a lot of interest in them. I showed the breast milk example, and the main core of this talk is waveome, is a software that allows to find the dynamics, temporal dynamics in your data, and what explains them in terms of the information you have about your samples. And it's very useful software when you have a longitudinal study to find the biomarkers in your study. We have some, this work is stable. This software is, you can use it, but we have some improvement from our end that we are adding. So we making the kernel search more optimized. So this work has been supported by NSF, and that's the award number. And the data I showed is from our collaboration with NIH, and these are my group that they contributed in this, mainly led by Alan Russ. Thank you.
I think we may have time for one question. If we have a question, no?
So if you run it on your computer, it takes maybe 8 hours or more. It's a very time-consuming approach, but we recommend to you run it on your high-performance computing if you have one. So what is a very time-consuming approach. That's part of the optimization we are doing, and the prior kernels, yeah. If you reduce the number of metabolites and rank them, and let's say, because it runs one by one for each metabolite, if you do it for few, it's going to be fast.